welcome back to the second half of this lecture, and in the earlier part we have seen the map VL defined, and we have also checked that not every subset of L power n can be an affine algebraic K set, but this one if you take a finite field then it will be correct. This I will prove it leisurely after some time, but I just want to say it can be surjective when K is a finite field. But there usually in case of finite field the topology and geometry will not play much role because everything is discrete there. This explanation will make much more sense once I define a topology. So, wait for that. But I want to see some examples so that you can get a good feeling. So, let me again write some examples. And I will take these examples will contain some observations which are also interesting. So, as usual my notation will be L over K field extension, and do not even assume that L is algebraically closed. L is also arbitrary. For definition we did not need algebraically close. Algebraically close I will need to decide when the VL is bijective. Okay, so I do not need, so all the earlier definition also makes perfect sense when L is arbitrary field extension of K. So that also option I want to keep it open, because I could also take some time L to be equal to, for instance L to be equal to, I could take field of rational functions Kx in one variable. For example, this is the field of rational functions in one variable x. Over K. This is also interesting study because more often you will for example subjects like complex analysis or Riemann surfaces, you will have to study field of rational functions because they will correspond to the meromorphic functions. Anyway, we will not deal in this course, that is just a side remark. Alright. So, example 1, linear K algebraic sets. So, that means I take the ideal generated by linear polynomials. So, let us denote Fi. Fi is a linear polynomial. This is by definition summation a I j x j minus b I is from j is from 1 to n. So, variables are x1 to xn, and these aij's and bi's they are in the base field K. So, this, and we are looking for what? We are looking for affine. This is true for all I equal to 1 to m and j equal to 1 to n. This is the setup, and VL is F1 to Fm. This is what? This is the solution set for this system of linear equation. It is a linear equations. So, this is a subset of L power n. So, this is called linear K algebraic set in L power n, defined by F1 to Fm, which have coefficients in k x1 to, these are elements in k x1 to xn. And if you remember, the whole linear algebra course centers around studying this, how to find it, how big is the set, and so on. So, I am going to write down precisely the solution now. And how do you write in linear algebra this? So, in linear algebra this is denoted short. This is, you put A to be the matrix Aij, this is, this coefficient will give you the matrix which is rows are 1 to m. So, this is m comma n coefficients in k, and all these equations they are written one after the other. So, they are written like this F1, F2 and so on Fm, and we are looking at, and then so this we write the coefficients here and the variables, and how do you get this? So, this is written as A times capital X, where capital X is the column x1 to xn, and when you multiply this, what you get is the column vector B, where this B is B1 to Bn, and this is given in k power n. But this matrix is also in n, and we are looking for solutions where we are looking for solutions in L power n. All right. And how do you write it, if you remember correctly? So, I will write it. So, this is described very nicely in algebra. All right. So, what is the solution set? So, it depends on, so I will, in linear algebra usually it was done when L equal to k. So, let us take that case, if just to compare what we studied earlier. So, if so if L equal to k, and if you remember R is the rank of this matrix, then V k F1 to Fr, F1 to Fm has D equal to n minus R linearly independent over k solutions. In fact, we may write down that precisely. In fact, we can write down this V k F1 to Fm in terms of the parameter. So, in fact, this is precisely called parametric representation. That is, this equal to one special solution, that is called x naught plus summation Ti xi, I is from 1 to D, where these T1 to Td, they are elements in K, they are the parameters. So, and this x naught and these xi's, x naught and then x naught, x1 to xd, these are in k power n, and you see these guys are linearly independent, x1 to xd are linearly independent, and this x naught is a special solution. These are in fact, these x1 to xd are in fact solutions of the homogeneous system of equations. That is how we describe them. So, this is the description, and therefore, you realize that in linear algebra you have to understand what is rank, what is dimension, and so on. So, all these things are coming into this. So, it is a part of this, very easy part of algebraic geometry, you can say. So, second example is what are called K hypersurfaces. That means what? We are taking the principal ideals, and when we saw above in one of the example, when you take principal ideals and you want to understand the 0 set of this single polynomial, we could always assume that this polynomial is a product of different prime factors. Such polynomials are also called square free. So, f is a polynomial, a single polynomial, f is only one polynomial, and to understand now VL of f, this is a subset in L power n, we may assume f is square free. Square free means f is a product of different prime factors, f pi 1 to pi r, where these pi 1 to pi r are polynomials pi I, they are polynomials with coefficients in k in n variables x1 to xn, and we are assuming they are monic and irreducible, and pi I is not equal to pi j, they are different. That is the meaning of it is square free. So, this is called hypersurface, K hypersurface. In L power n. It is defined by only one equation and given by with coefficients in k. So, for example, if you want to take n equal to 1, then we have a polynomial in one variable. So, obviously, what is VL of f, then we can write down VL of f will precisely be the 0 set of. So, this is all A in L such that f of a is 0. This is equal to the 0 set of f in L, and we know that it can have maximal how many elements. So, cardinality of VL of f in this case will be less equal to degree of f. It cannot have more than the degree zeros, but however, if I want to say equality here, see this inequality is very crude, it could be empty set, we saw it. So, it is sometimes better to say what is the, how do we count points here so that it becomes equal. So, the right formula is moreover or more precisely if I take degree of f equal to summation, summation is running over the 0 in L, and here this A should be counted how many times? Multiplicity times. So, new AF, and what is new AF? This is where where nu AF is the multiplicity equal to multiplicity of the 0 A of f. What is that? That means, so this is the same as, so that is x minus a power this nu AF, this is a factor of f, and the remaining one didn't have x minus a as a 0. So, that with f equal to x minus a power nu a f times g, and g of a should not be 0. So, this is the highest power of x minus a that can divide f. So, this means, this equality means two things. First of all the 0 of f lie in L, and if you count them properly, if you count a nu a times some other 0 b nu b of f times and so on, then you get equality. That is a nice formula. How do you find this nu f of f? You do not have to factorize it. So, the usually in analysis you find, no, if a is a 0 of f, then how to find the multiplicity nu a f? This is found like this. Look at f, we know f of a is 0 because it is a 0 of f, and go to the derivative of f. If f prime of a is still 0, that means nu a f is at least 2, and keep doing this. So, when it comes f nu minus 1 is derivative at a is 0, but the next one, that f nu at a is non-zero, test all these derivative vanish or not. The first time you hit upon where the derivative does not vanish, then this nu equal to nu a f. This is a test without a factorization. This is very important to find calculation. All right. So, then the third one now. How many points an hypersurface can have, whether it is finite, infinite and so on. So, this third it gives an observation about hypersurfaces. So, if L is infinite field, infinite, and n is bigger or equal to 1, then every hypersurface, so look at the hypersurface and look at its complement Ln minus VL of f, where f is a single polynomial in n variables. This is the complement of a hypersurface. So, this is a complement of the hypersurface, this is also infinite. Okay, so let us see what it means. So, L infinite is very important. See, if L is not infinite, L power n itself is finite. So, therefore, infinite, non-infinite, I mean everybody is finite. So, there is no question of infinite. So, and as I said, usually for getting the best result in geometry, we need to assume L is algebraically closed, and you know that algebraically closed fields are always infinite. L algebraically closed then L is infinite. This is true without non-algebraically closed also. For example, field of real numbers, field of rational numbers, they are also infinite. So, if I have to draw the picture, let us draw a picture. So, okay. So, the specific thing in mind is the following. So, for example, let us take hypersurface in two variables. So, f x y in two variables over a field k. K may not be infinite, k may be finite, but L is infinite. For example, you could take finite field and algebraic closure of a finite field. And what do you want to draw? We want to draw this V L of f. This is the pair now. I will denote pair A comma B in L2, n is 2, such that f of AB is 0. This is the hypersurface in L2. For example, you could have taken f equal to y minus x square, and the picture I would draw. Now, this is a two dimensional vector space over L. For example, you could take k equal to L equal to real numbers, then this will be a parabola, right. This is precisely f equal to 0. The 0 set is precisely this. This is called parabola. And what is our statement we want to prove? We want to prove that L2 minus VLF is infinite. This is what we want to prove. We will prove of course general, but you see it pictorially. Here are so many points which are not on this parabola. So, there are many points outside, right. All these points are outside and they are in this complement. Alright. So, that is pictorially it look obvious, but the proof are not accepted pictorially, because this picture is only a intuition and it is not very rigorous. So, let us prove now. What we are proving? We are proving that, so to prove in general, to prove Ln in general, Ln minus VL of f is infinite. That means I have to produce infinitely many points. That means I have to produce infinitely many points in L power n which are not 0 of f. Alright. So, what do? We have a polynomial given. So, right. So, I am going to prove this assertion by induction on n. On n. So, n equal to 1, let us see what we have to prove. L equal to 1, that is L minus VLF is infinite. That is what we want to prove. But L is infinite and this VLF just now we saw is a finite set for one polynomial, only one variable polynomial, only finitely many zeros. So, only from L we have omitted finitely many points. So, therefore, it is clear. So, this is clear. Alright. So, assume n is bigger equal to 2. Alright. Now, what can you do? We have polynomial in many variables and you consider that polynomial is in the last variable and coefficients in the remaining variables. So, that means we are write f equal to f0 plus f1x xn plus f d xnd. So, where this d is the degree of the polynomial f in the variable x n, and these f i's are actually polynomials in x 1 to x n minus 1 with coefficients in k. That is how this polynomial looks. Now, it is only one variable polynomial, and this because this d is this, so f d, this polynomial f d is non-zero. Now, we have one polynomial in less number of variables. So, by induction hypothesis we can definitely find many infinitely many zeros, not zeros, infinitely many points in ln minus 1. So, by induction hypothesis I have to go to the next page. By induction hypothesis, there exist, or the set, the complement L n minus 1 minus V L f d, this is infinite. Because it is a non-zero polynomial, and so I want to make sure that I have next one. So, here in this assertion we need to assume the polynomial is f is non-zero, because if f is a zero polynomial has everybody is 0. So, this will be actually empty set. Alright. So, let us continue. So, because this is a non-zero polynomial, I can apply induction hypothesis, and this is infinite. Alright. So, this is infinite, that means I can always find a point. So, that is there exists somebody in L n minus 1. So, a 1 to a n minus 1 in L power n minus 1, such that with, when I, this cannot be 0 of this polynomial, f d of a 1 to a n minus 1, this is non-zero. There are infinitely many points in L power n minus 1 where f d does not vanish. So, I choose one of them, let us say, and then I substitute. Alright. So, now I substitute. So, what is f? Original f evaluated at, I substitute x 1 equal to a 1, x 2 equal to a 2, etc., x n minus 1 equal to a n minus 1, and x n I want to keep it as it is. So, this is equal to then f 0 a 1 to a n minus 1 plus f 1 a 1 to a n minus 1 times x n, and the last term is f d a 1 to a n minus 1 times x n power d, and I have chosen these a 1 to a n in such a way that this is non-zero. And now I have a polynomial in one variable with coefficients in L. So, in any case this polynomial will have, so this is a polynomial in L x n in L x n. See, because I evaluated this substitution will land you in L and not in K in general. So, this is anyway L is a field, one variable polynomial. So, it can have at most finitely many zeros. So, and L is infinite. So, I can choose the last coordinate many times, infinitely many times. So, choose, so there exist infinitely many n in L such that f of a1 an minus 1 an, this is non-zero. See, this is a non-zero polynomial because this coefficient is non-zero and it has finitely many zeros in L. Therefore, I can choose many n's which are not zeros. So, therefore, I will get this non-zero. So, that means this a1 to an minus an to an minus 1 comma an, this is a point in Ln, but not in VL of f, and these are these the last coordinate already infinitely many possibilities. So, therefore, that proves the assertion. So, what we proved is if L is infinite field and n is at least 1, then the complement of a hypersurface is always infinite. Now, the next assertion I want to show is what happens on the hypersurface. So, that is also easy. So, let us formulate and prove it. So, this is the fourth observation. So, now f is again, now I assume. So, now you will realize why one need to assume L is algebraically close. Algebraically close. And n is at least 2. Also, n equal to 1 will not work because n equal to 1 polynomial in one variable will always have finitely many zeros. So, we cannot talk about infinite set, infinite algebraic set. So, then every K hypersurface V L F, f is a non-zero polynomial in n variables with coefficients in K. Contains infinitely many points. So, what does that mean pictorially? So, if you have n equal to 2, let us say, then, and suppose we have taken a circle, this equation is x square plus y square equal to 1 or plus 1 equal to 0 or minus 1 equal to 0. This has infinitely many points. Our field is now C. For this R will also work, but I want to show why L algebraically close is very important. It is necessary, this assumption. Let us see another example. Now, let us take the equation, the polynomial f. So, this was one example. Other example was f g or h equal to x square plus y square plus 1, and I am still in R x y. So, what is V R H? This is empty set. There is no pair A comma B of real numbers, so that H of A B is 0, because what is H of A B? H of A B is A square plus B square plus 1 equal to 0. That is what we want, but that means A square plus B square equal to minus 1. That is not possible in real numbers, because this side is positive, that side is negative, not possible in real numbers. So, therefore, this we have proved. So, in this algebraically close is important, and if you see now, if you take K equal to R, K equal to R, K equal to R and L equal to C, then what is VL of x square plus y square plus 1, there are many points. So, this is plus, I have to draw neatly, this is plus, this is plus. So, what are the some points? Let me write some points. For example, x equal to 1 and y equal to I no x equal to, so what do we have to solve? Let us write down precisely. That means if I want what, x comma y, so this is like, so you see, you fix 1, for example y is 0, then you can take x equal to minus I, or you can fix y is any complex number and then you solve every complex number as a square root, we know. So, therefore, this is infinite, is infinite. Check this, that you will use the fact that every complex number z has a square root in C. All right. So, let us finish up this proof. So, proof of this, first of all, note that L algebraically closed, so L is infinite. L is infinite. And n is at least 2. So, you can always write as earlier proof f equal to f0 plus f1 xn plus f d x power n xn power d, where this f d is non-zero and these are polynomials f0 to f d, they are polynomials in one lesser variable over k. So, that is at least one variable. So, I can always find a point so that this is non-zero, because that is earlier proof, this is infinite. So, I am applying. So, there exists a1 to an minus 1 in L power n minus 1 with f d of a1 to an minus 1 is non-zero. Now, what do I get? This polynomial I get f of a1 to an minus 1 comma xn, this is a polynomial non-zero of degree d, because this coefficient is non-zero. So, you can always find, because L is algebraically closed, this is a polynomial now in Lxn. So, this is polynomial in one variable over L. So, it always have a 0. So, let me go to the next page. So, there exists an in L such that f of a1 to an minus 1 comma an, this is 0, since L is algebraically closed. So, what does this mean? So, this means, so that is this point a1 to an minus 1 comma an, this point is in V L of f. Alright, and how many possibilities were there for a1 to an minus 1? These were the infinitely many possibilities. Therefore, these are infinitely many possibilities. Therefore, altogether infinitely many possibilities. So, it proves VL of f is infinite. So, that means there are enough points on the hypersurface provided L is algebraically close. Alright. So, with this I will stop, and in next lecture I will define a topology on this L power n. That is I will use ideals to define a topology, and I will recall some definitions etc. of topology, and we will now then head to prove when this map VL is bijective. For that I define a map in the other direction and try to check that this map is the inverse of that map. But this will take for a while, but this is the beginning, it is the cornerstone in algebraic geometry. This is called Hilbert-Snow standards. So, with this I will stop today, and we will continue in the next lecture. Thank you very much.